I've asked Chuck Moore to give a presentation today on Forth, and he's going to talk about his experiences with his language for the last 15 years. So if I can introduce Charles Moore.
That's quite a broad topic. How long are we talking?
15, 20, half an hour, whatever you'd like.
Tape runs?
Tape will run for an hour, so as long as you'd like.
Okay. 15 years. That just about covers my experience with computers as opposed to software. Going back 15 years, the motivation for switching the emphasis from Forth the language to Forth the microprocessor was twofold. First, the software problems were solved. It was easy to write applications, trivial to write applications. All the problems lay in the hardware. Hardware was awkward, messy, unreliable, especially if you were dealing with a custom system that someone had built for which they wanted custom software. It became a real drag to try to debug the hardware for them. And it became clear that the hardware engineers weren't doing a very good job. Better than the software engineers in the industry, but not as good as software engineers with Forth. So I thought I would see what I could do to address the hardware problem. That might have been a mistake. Forth is a lot of fun to work with. Hardware is not so much fun. Don't know if you are all aware of the history, but the first Forth processor that I did, it might have been the first one at all, was a Novix, which was a 16-bit. State of the art as far as speed is concerned, meaning 8 MIPS. And it was a lot of fun to work with. We got a really nice Forth on it, CM4. Much smaller, simpler than the other Forths have been doing for Forth. And then, of course, Shaboom, which was 32 bits. And 50 MIPS. And now the I-21 is the latest incarnation, which is 20 bits. And I like to claim 500 MIPS. Each of these had its own Forth kind of associated with it. The goal was very simple. First, to minimize the complexity of the hardware-software combination. As far as I can see, no one else is doing that. Some lip service, perhaps, but no one is trying to minimize the complexity of anything, and that is a great concern to me. We're building a culture which cannot survive as trivial an incident as Y2K. Once we lose the billion-dollar fabrication plants, once we lose the 1,000-man programming teams, how do we rebuild them? Would we bother to rebuild them? Are computers worth enough to demand the social investment we put into them? It could be a lot simpler. If it were a lot simpler, I'd have a lot more confidence that the technology would endure into the indefinite future. There seems to be a propensity to make things complicated. People love to make them complicated. You can see that in television programming, you can see it in products in the marketplace, you can see it in the internet websites. Simply presenting the information is not enough. You've got to make it engaging. I think there perhaps is an optimal level of complexity that the brain is designed to handle. And if you make it too simple, people are bored. If you make it too complicated, they're lost. I'm never bored by simplicity. I'm entranced by it. If you can show me a simpler way of doing any of the things I'm doing, I will jump on it. But that doesn't seem to be the case. Automobiles, airplanes, spacecraft, immensely complicated devices. Forth doesn't need to be complicated. Classic Forth started out simple. It gradually accreted layers of complexity. And at Forth Inc., that kind of became the company culture. We had this package, and we were selling it, and we were exploiting it, and we were stuck with it. When I left Forth Inc., I had a chance to simplify. And CM Forth was the result. Unfortunately, CM Forth didn't get used for a lot of applications, so it's hard to tell how well it would have worked out. The Forth I did on Shaboom was, as I recall, pretty much like CM Forth. The biggest application I did was to make video work and to start the process of the custom silicon design package. So I know that the approach worked well with Shaboom. I-21, the Forth I'm using there is ColorForth, and I haven't done any significant applications on it yet. It is brutally simple. It is simpler than any of its predecessors, and I can say a little bit about it and why. The I-21 itself is a simple processor. Not as simple as it could be, because it seemed to me the only hope we had of selling a processor was to make it fast. So I've added a lot of complexity in order to gain performance. Hopefully I've found some kind of reasonable balance. 500 MIPS is a very nice speed. This we can only do with burst at the moment, but it will become a sustained speed someday. The problem is there are no applications that require that much speed, or require a large number of processors running at that speed. It's a hard sell. The most encouraging application I've seen recently is the SETI at Home project, where you can download data from Arecibo, process for a couple weeks on your PC, send it back to them, participate in this exploration. So maybe a faster processor would sell there simply for that application. You get a SETI distributed processor system. Maybe there are things you can do. But once you've got a processor, hopefully one well suited for Forth, then the question is, what should Forth look like in order to exploit the processor? And that raises the question, what is Forth? And I have hoped for a long time that someone would tell me what it was. I keep asking that question. But what is Forth? Forth is highly factored code. I don't know anything else to say except that. Forth is definitions. If you have a lot of small definitions, you're writing Forth. In order to write a lot of small definitions, you have to have a stack. Stacks are not popular. It's strange to me that they're not. There's just a lot of pressure from vested interests that don't like stacks, they're not registered. Stacks are not a solve all problems concept, but they are very, very useful, especially for information hiding. And you have to have two of them. These ideas have been around for 30 years now. I have been promoting them for 30 years. Their level of acceptance is about where it was 30 years ago. Perhaps even less, considering that the industry has expanded so much. So that is Forth, and this is a requirement to support definitions. What is a definition? Well, classically, a definition was colon something, and words, and the definition symbol. I always tried to explain this in the sense of it's an abbreviation. Whatever this string of words you have here that you use frequently, you've given it a name and now you can use it more conveniently. But it's not exactly a definition, an abbreviation, because it has a parameter perhaps, or two. And that is a problem with programmers. I guess it's perhaps a problem with all programmers. Too many input parameters to a routine. Look at some C programs and it's ludicrous. I mean, everything in the program is passed through the calling sequence, and that is dumb. The fourth word should not have more than one or two arguments. This stack, which people have so much trouble manipulating, should never be more than 3 or 4 deep. So, a current incarnation of a word is to make it red. That way, you don't need to use the colon. And this not only reduces the amount of text you have to store in your source file, it vastly clarifies what's going on. The red word is being defined. The definition actually is green with, I feel a green marker. The definition is green. You might have a semicolon in the definition, which means return, but it does not mean end of definition. So you can have more stuff in another semicolon if you like. And you can have another entry point here if you want. So without this semicolon, this definition will fall into this definition and will return at this point, but still, there's no state in the sense of you are in compile mode as opposed to execute mode. You're either running green or you're running white background, you're running black. Black means execute, green means compile, red means define. This to me is simpler and more clear. Whether it gets any, it's brand new, so it hasn't got any acceptance. We'll see. But as to stack parameters, the stack should be shallow. On the I-21 we have an on-chip stack of 16 deep, 18 deep. This I chose as a number effectively infinite. The words that manipulate the stack are dupe, drop, and over. Period. There's no, well, swap is very convenient, and you might, in a sense, you got to swap. It's not a machine instruction, though. But no pick, no roll, none of the complex operators that let you access down into the stack. This is the only part of the stack, the first two elements, if you have any business worrying about it. And of course, on the chip, those are the inputs to the ALU, so the two top elements are the ones that are relevant to the hardware. The others are on the stack because you put them there and you're going to use them later, after the stack falls back to their position. They're not there because you're going to be using them now. And you don't want too many of those things on the stack because you're going to forget what they are. So people who draw stack diagrams or pictures of how the stack is, the things that are on the stack, should immediately realize that they're doing something wrong. That is not, the stack should not be that complicated. Even the little parameter pictures that are so popular. If you're defining a word and then you put in a comment showing what its stack effects are, that takes X and produces Y. I used to appreciate this back in the days when I let my stacks get too complicated, but no more. You don't need this kind of information. It should either be obvious from the source code or documented somewhere else. So the stack operations I use are very limited. Likewise, the conditionals. In classic Forth, we use if, else, then. And I've just eliminated else. I don't see that else is as useful as the complexity it introduces would justify. So typically, I mean, you can see this in my code. I will have if with a semicolon, and then I'll exit the definition at that point or continue. So I have the two-way branch, but using the new feature of a semicolon which does not end the definition. Likewise for loops, there have been a lot of loop constructs. The ones I originally designed were taken out of existing languages. I guess that's the way things evolve. There was do loop. There was for next. There was begin until. This was from Fortran. This one was from Basic, I think. This one was from Algol. What one do we pick for Forth? This has two loop control parameters and is just too complicated. This has one loop control parameter and is good for the hardware implementation. It's simple enough to have a hardware implementation where this one's not. And this has variable numbers, maybe some, maybe none. Unfortunately,
I need to go to a meeting.
We are borrowing this recording facility from ITV. It is their vault, conference room vault, and if you hear an echo in the sound system, that's why. It's a vault. I've got a new looping construct that I'm using in ColorForth, and I find it superior to all the others. And that is if I have a word, I can have in here some kind of conditional with a reference to word and other stuff. And this is my loop. I loop back to the beginning of the current definition. And that's the only construct I have at the moment. It seems to be adequate and convenient. It has got a couple of side effects. One is that it requires a recursive version of forth. In other words, this word must refer to the current definition and not some previous definition. This eliminates the need for the smudge-unsmudge concept, which ANS is talking about giving a new name. But the net result is it's simpler. It would, of course, not be convenient to nest loops. But nested loops are a very dicey concept anyway. You may as well have nested definitions. We've talked over the last 15 years about such things. Should you have conditional execution of a word, or should you have something like if-then? Well, here's an example where I think it pays well in clarity. The only loop you have is to repeat the current word. And you can always do that. It leads to more intense factoring. But that is, in my mind, one of the keystones of forth. Is you factor and you factor and you factor till most of your definitions are 1 or 2 lines long.
You might point out that the semicolon after word results in tail recursion and converting the call in word to a jump.
Ah, yes.
And therefore, that's how the loop functions.
Yes, this is I think it's convenient notation because it shows you what you're doing. You're going to go execute word and then you're going to return. So there's no reason to make that a call since you're never going to go anywhere. You're going to do a jump. In fact, in all my latest forths, semicolon kind of meant either return or jump depending on the context. And it's optimized by the compiler to do that. Very, very simple look-back optimization that actually saves a very important resource, the return stack. Now on the I-21, the return stack is only 16 deep and 17. And people who are used to nesting indefinitely might get into some trouble there. You shouldn't nest too deeply. It makes programs impossible to follow. You can have spaghetti code with calls as easily as you can have spaghetti code with go-tos. And you've got to keep it simple. As I recall, those are the major changes I've made to my current forth. Maybe with the exception of addition of block. Block is a wonderful word. It's always in the best compute. Block used to access a region of disk. Now I define it as accessing a region of memory. There's no reason to use disk at all. With megabytes of memory available, you just load your disk into memory and access it there. So block becomes much, much simpler. It's basically, the definition of block is 1,000 times. It gets you access to a block of memory, which is 1024 bytes wide. You can index inside it. The value of block is that it partitions your memory for you, factors your memory into manageable pieces. You can talk about, instead of a megabyte of memory, 1,000 blocks of memory, and you're dealing with smaller numbers. I encountered a NASA web page just today, which is amusing. They spoke of, I think it was 69 110,000 kilometers per hour. This was the speed of the spacecraft, Stardust spacecraft. Conveniently, since I don't really have any good feel for that number, they converted it into 69,000 miles per hour for the convenience of people who don't think. And those numbers are both too large to have any meaning to anyone. It probably comes down to something like 10 kilometers per second, some nice small number that I can get some feel of, that I can compare with other numbers that I can remember. It doesn't do any good to let the numbers get big. And when we're dealing with 128 megabytes of memory, just begging to let the numbers get big, it's impressive, but it isn't helpful. So blocks help restore things to a human scale. Now, in the course of saying those things, it occurred to me that there's something else I wanted to say, and I forgot what it was. Well, one thing is to say that Forth is what Forth programmers do. I would like to think of it as what Forth programmers ought to do, because I've found that teaching someone Forth does not mean he's going to be a good Forth programmer. There's something more than the formalism, the syntax of Forth, that has got to be embedded in your brain before you're going to be effective at what you do. My contention is that every application I have seen that I didn't code has got 10 times as much code in it as it needs. And I see Forth programmers writing applications with 10 times as much code as is necessary. And the concern I have, the problem I've been pondering for the last few years is how can I persuade these people to write good Forth? How can I persuade them as possible to write good Forth? Why would anyone want to write 10 times as much code as they need to write? Microsoft does this, I'm sure we are all aware. But they almost have an excuse for doing it, because they're trying to be compatible with everything they have ever done in the past. And if it is impossible for you to start on a clean sheet of paper, you're going to have to write more code than otherwise. But 10 times as much code? That seems excessive. How big should a program be? For instance, how large should the TCP/IP stack be? I don't know. I couldn't know without sitting down and writing the code for it. But it should not be very big. Kilobyte maybe. A kiloword. Now, the i21 has 4 instructions per word. The Pentium has 1 instruction per 2 bytes. It's very hard to judge. You should talk instructions instead of the size of the memory in which the instructions reside. About 1,000 instructions seem to be about right to me to do almost anything. The old, if I paraphrase, the old legend that any program with 1,000 instructions can be written in 1 less. All programs should be 1,000 instructions long. How do you get there? What is the magic? How can we make an application small? Well, you can do several things. that are proven to do in any case, and in any language. One is no hooks. Don't leave openings in which you're going to insert code at some future date when the problem changes, because inevitably the problem will change in a way you did not anticipate, and the hooks are useless. Whatever their cost is wasted. Don't anticipate. Just solve the problem you've got. Simplify the problem you've got. Or rather, don't complexify it. I've done it myself. It's fun to do. You've got a kind of boring problem, but just hiding behind it is a much more interesting problem. So you code the more interesting problem, and then the one you've got is a subset of it and falls out trivially. But of course, you wrote 10 times as much code as you needed to in order to solve the problem you actually had. 10 times code means 10 times cost of writing it, the cost of documenting it, the cost of storing it in memory, cost of storing it on disk, cost of compiling it, cost of loading it. Everything you do is going to be 10 times as expensive as it needed to be. Actually worse than that, because complexity increases exponentially with size. 10 times the bugs, or worse. And 10 times the difficulty of doing maintenance on code, as is amply illustrated by the Y2K bug. In fact, it's curious, the fixes that I've seen people making to COBOL programs, for instance, to fix the Y2K bug, make the program significantly more complex and larger, and leaves the spaghetti code, which can't be maintained. It's probably going to fail again in 50 years, because they're putting in windows. They aren't increasing the range of the date. They're merely shifting the origin of the code. And that's going to lead to another problem when that window runs out. This is why we're still running programs that are 10, 20 years old. Why people can't afford to update, understand, rewrite these programs, because they are significantly more complex than they need to be. 10 times more complex than they need to be. So how do you avoid falling into this trap? How do you write one-time programs? Oh, there's a name for a web page. One-timers. You factor. You factor and you factor and you factor and you throw away everything that isn't reused, it doesn't justify. The whole point of Forth was that you didn't write programs in Forth, you wrote vocabularies in Forth. And when you had an application, you devised 100 words or so that discussed the application. And you used those 100 words to write a one-line definition that solved the application. That works very well. It is not easy to find those 100 words. But they exist. They always exist. Let me give you an example of an application in which not only can you reduce the code, the amount of code required, I'm saying you can reduce the code by 90%. And here's a case in which you can reduce the code by 100%. And it's a topic dear to our hearts. It's called files. If you have files in your operating system application, in your Forth system, you have words like open, or maybe close, and read, and write, and rewind, and whatever. And they aren't usually such long, nice short words. They're like open file, closed file, because there's all kinds of things you can want to be opening and closing windows. If you can realize that this is all unnecessary, you save 100% of the code that went into writing your file system. Files are not a big part of any typical application, but it is a singularly useless part. And by identifying those aspects of what you're trying to do and saying, we don't need that. We don't need checksums on top of checksums. We don't need encryption because we aren't transmitting anything that has the slightest level of interest to anyone else in the world. We can eliminate whole chunks of things. Now, the general solution to a problem, of course, requires all the facilities in the world and more. And that is what all of the programmers in the world are out there inventing for you, the general solution. Nobody has the general problem. Answer. I wish I knew what to tell you that would lead you to write good Forth. I can demonstrate. I have demonstrated in the past as nauseam applications in which I could reduce the amount of code to at least 90%, sometimes 99%. It can be done on a case-by-case basis. The general principle still eludes me. What can I say?
I had a question about your screens in ColorForth. People have commented that you have a very large font and very little information on the screen. What amount of that is because of your vision, and what amount of that is because you believe it's useful to limit the amount of information you're looking at one time?
Yes, I'm losing patience with small characters. Very, very hard for me to read web pages because with my eyes, the characters are blurred. With my reading glasses, the characters are blurred. If I increase the character size, which sometimes I can do and sometimes I can't, I lose the amount of information. I'm losing a lot of context, so that's not good. It's a problem. It's probably a problem for an increasing fraction of the population. So I make the characters as big as I can. But Jeff's right. As soon as you make them too big, you lose information. Now, it's a classic rule of thumb for designing slides. So you pick a frame and you put up some bullets and topics, and you don't try to put too much information on a slide, because you will only confuse your audience, and if you make the characters small, they won't be able to read them either. So that is of interest to me. In the case of ColorForth, I think my characters are probably too large. I can get 256s on the screen at once. It's 20 by 14 or sometimes 24 by 15. Depends on exactly what computer I'm using. That is enough. In this 256 bytes, I'm getting about as much information as I used to get in 1024 byte screens. Because I'm not doing any formatting. I'm not even doing any word wrap. I'm just packing the screen densely with characters. One reason is that I want to explore the value of the color words. If I've got some colorful words here and different encoded text and stuff, how does that stand out? I find it works very well. That I don't need to format this with all defined words at the left. In fact, that might be actually ugly because then I've got a wall of red on the left, and if it's all organized that way, then it doesn't need to be red. So it's trying to take advantage of the color in a way. I do feel that when you're putting up a web page, for instance, you should take much more of this philosophy. Put as little information on the web page as you have to, in order to make it clearer what you're trying to say to people. Don't get wordy about it. On the other hand, don't put up a web page as an index that you have to go jump to other web pages. That's just a nuisance. You want to put up real information. You want to highlight the information that's important. But you want to make it clear and readable. I think it isn't easy for me to change my character size, which is why it's the way they are. They're 32 by 32 pixels. I would probably go to 24 by 24 pixels next time I try it. In this form, an application is rarely one screen. An application is probably 2 or 3 screens. And that is about as much code as I would write for an application within a context. For instance, I have an application which puts up spectra on the screen relating to the performance of a particular chip. And that application, I think, takes 4 or 5 of these screens. It's nice, colorful spectra. And it's an exercise in presenting information in an understandable and pleasant way. If you get a chance to see a demo of that sometime, it would be fun. Small application, if application is the right word. Small bits of code which do a particular thing and are not generalizable to do anything else. That's my style.
Okay.
See, Jeff has reminded me of a couple other concepts in machine forth. Machine forth is what I like to call using the forth primitives built into the computer instead of interpreted versions of those with defining macros that use those. One of them is if. Classically, if drops the thing that's on the stack. And this was inconvenient to do on the I-21. So if leaves its argument on the stack, and very often you're obliged to write constructs like if drop. But not always. It seems that about as often as it is inconvenient to have if leave its argument on the stack, it is convenient for that to happen. It avoids the need to construct a dupe if, or a question dupe if. So with this convention, the need for question dupe has gone away. And question dupe is a nasty word because it leaves a variable number of results in the stack. And that is probably not a wise thing to do. In addition to if, the machine forth has a minus if. And this if is testing for 0 or not 0, and this one is testing for the sign bit only. It was my thinking that very often you're going to make a decision on whether a number is positive or negative. It hasn't worked out that way. ColorForth, I don't even bother to use this instruction. The world has changed in the last 20 years in ways which maybe are obvious, but I don't think anyone anticipated. When I first started in this business in '57, computers were used for calculating, computing. And the applications in those days usually involved large, long, complex algebraic expressions. And the factorization that you did was to factor out those parts that didn't have to be recomputed, so the whole thing would go faster and it would be. And that was the whole point of Fortran. And that tradition has stuck with us even today. When I don't know the statistics, but I would guess that most computers do not compute. They move bytes around. If you have a browser, your browser is not calculating anything, except maybe the limit of what will fit on the screen at some point in time. So this concept of looking at the sign of a number is not as useful as I expected. Almost all numbers are positive, so there's no sign to look at. For the same reason, machine Forth does not have a subtract operator. I use this symbol to mean one's complement. And with only a one's complement, it isn't even very easy to do a subtract. But the point is, you don't need to do subtracts. For today's applications of implementing protocols or displaying text, arithmetic is not necessary. So a computer should not be optimized for arithmetic, and mine are not. On the other hand, in order to optimize data transfer, it is very useful to have an incrementing fetch operator. One of the problems on the, I suppose on any computer, but it's particularly apparent on the I-21, is addresses. An address is a 20-bit number. To load an address, you pretty much have to do a literal fetch, which takes an extra 20-bit word, takes an extra memory cycle. To load the address, and then you can do the fetch against the address, which is going to take another memory cycle. So the manipulation of addresses is expensive, and you want to do it as little as possible. Fetch plus helps that way. You put an address in the address register, which is called A, and it stays there for a while. And if you execute this operator, A gets incremented by 1, and you can fetch a sequence of things in order. Likewise, there's a store plus. And of course, there has to be a fetch and store that don't do the increment for when you need them. These operators are not in classic Forth. I don't think they're even mentioned in the standard. They lead to a completely different style of programming. In the case of a do loop, the efficient thing to do is actually put the address on as your loop control parameter, and then refer to it as I, and do an I fetch inside the loop. And the do loop is working with the addresses. If you don't do that, if you have the fetch plus operator, instead, then you don't need the do loop, you don't need the I, and you use the fetch plus inside your loop to fetch this different thing each time. It's different but equivalent. You can map one to one from one domain into the other. But in addition to the notion of having to fetch something whose address is conveniently stored in the A register, in the case of move, where you want to move something from one region of memory to another, you have to have two addresses available. Hence the value of being able to reference an address stored in the R register. And since that is probably the only context in which you're going to be using the R register, it has an automatic increment associated with it. So we've got basically a fetch plus against A and a fetch R against R, or store R, and then you can do a move operator efficiently. But
Okay.
back on record, A brings up another issue. A acts very much like a local variable. It's a place where you can store something for a while and retrieve it later, in addition to acting as an address register. The reason it acts as an address register, the reason I have it as an address, is literally to provide a mechanism for this. It is more convenient for the address to be on the stack from a programming standpoint. But if you're going to execute repetitively, you have to put it in a place where you know where it is. In order to put it there, you have to be able to access that register. If you're going to do that, you can use that register for other things. Just like we can use the return stack for other things. The difference is, when you put something on the return stack, you have to take it back off again when you're done. You can put it in A and it'll go away, you don't care. There has been a temptation to make A into a stack. So you could push several things into A and pop them back off again. It's never been clear that that was worth the cost of doing. It would require more instructions to access A. Do you want to be able to do A? Do you want to be able to drop A? It's so far been easier to just leave A as long as it is. I would very much like another register, which I'd probably call M, to hold a multiplier in doing a 40-bit multiplication. But I've never had enough multiplies in the system to be worth doing that, so it hasn't happened. But such registers raise the question of local variables. And there's a lot of discussion about local variables in just about any Forth context. And that's another aspect of your application where you can save 100% of the code. I remain adamant that local variables are not only useless, they are harmful. And if you're writing code that needs them, you're writing non-optimal code or ready code. Don't use local variables. Don't come up with new syntaxes for describing them or new schemes for implementing them. You can do all kinds. You can make local variables very efficient, especially if you have local registers to store them. But don't. It's bad. It's wrong. It is necessary to have variables. ColorForth has got a whole slew of system variables or something that are necessary. And it is very useful when you're editing something to have a cursor position stored in a variable so that when you come back to it, the cursor there is still there and you can pick up where you left off. Variables are essential. I don't see any use for a small number of variables. And I don't see a use for variables which are accessed instantaneously instead of normal memory access. It's an exercise in cleverness in interpreting the stack diagrams and assigning names to them. You can play all kinds of games here. I think perhaps Forth programmers play too many games with the tool they have because there's no applications much better that Forth programmers concentrate on writing the applications than on refining the tool. And to me, the application du jour is a web browser. If you've run out of things to do, well, write a web browser. Netscape did not have the last word in what it should be or how it should look or what it should do. In fact, Netscape and Microsoft both borrowed heavily from the Mosaic browser. It's as if there was only one browser written. It's as if there was only one language written, and that was Fortran. Invent a better browser. It's a good application. It gives you access to a world worth of information. It's a good application. And it's one that I'm trying to focus on in my spare time. So for those of you who are listening or who have listened all the way through this tape, thank you. Goodbye.
Thank you, Chuck.